Modern processing facilities, particularly refineries and chemical plants, make products in a continuous stream. For the finished products to meet the specifications set for them, the variables in each process must be rigidly controlled. A process variable can be defined as a process condition that can change during a processing operation. Temperature, pressure, flow, and liquid level are the four most common process variables that can be found in almost any process situation. We said that variables can change during a processing operation, but in every process there is at least one variable, and usually more, that we want to keep at a specific value while the processing goes on. Regular laboratory analysis of processed products will determine if the variables we want to control are staying on specifications. But instruments like these have the job of actually measuring and adjusting the process variables and keeping them on target so the end product does meet specifications. A group of instruments that works together to control one or more variables in a process is called the instrumentation for that process. Process operators are responsible for keeping a process operating according to specifications. Operators need to know what jobs instrumentation performs and what the instruments can and cannot do automatically. Let's start by looking at some examples of why exact control of process variables is necessary. These heat exchangers cool the fluid output of one process before the fluid is introduced into another process stream. The fluid must leave the exchangers at a temperature that falls within a controlled temperature range. Otherwise, the process the fluid is mixed into may not meet specifications. Let's say the fluid to be cooled is oil and the cooling medium is water. The hot oil flows through tubes inside the exchanger. The cool water flows across the tubes and absorbs heat from the oil. A valve controls the rate at which water enters the exchanger. If the water flows too slowly, it won't carry away the heat fast enough. So regulating the flow of water is necessary if we want the oil within a certain temperature range. This distillation tower requires specific top and bottom temperatures so the feed will divide into the desired products. If tower temperature is too hot, many heavy components will vaporize, causing the top product to be off specifications. Some of the vaporized fluid leaving the top of the tower is cooled, condensed, and circulated back to the upper tower trays. This recirculated fluid is called reflux. A valve controls the flow of reflux into the top of the tower, and this helps regulate tower temperature. This fractionator is similar to the distillation tower we showed. A specific pressure range must be maintained inside the fractionator because an increase in pressure will increase the boiling point of the liquid feed. Any change in boiling point changes the rate at which various liquid components vaporize. So a change in fractionator pressure could produce too much of some products and not enough of others. One way to control this pressure is to regulate the flow of light vapors from the top of the vessel. Increasing the flow of vapors will reduce vessel pressure. Decreasing the flow will increase vessel pressure. This vessel provides a reservoir of fluid for a process. A minimum fluid level must be maintained or the vessel may be pumped dry. Vessel level is kept constant by measuring fluid level with a float and regulating outflow with a valve. In the four examples you just saw, keeping a process variable at a specified value or within a certain range of values was essential. And in each example, a valve regulated the flow and kept the process variable at its specified value. Regulating flow is a common way to control the variables in a process, but a valve is only one of the things we need. In any control situation, whether the equipment is a process furnace or a home heating furnace, there are 4 things that are necessary. First, there is a process that needs measurement and control. For each process variable that must be controlled, there is a measuring means, one or more instruments that can measure the process variable. There must be some kind of control mechanism to receive the measurement information and determine how it compares with the desired value or set of values. The control mechanism must also tell the valve what action, if any, the valve should take. And there is a final control element, which is usually a valve. The final control element makes the actual process change that keeps the process variable on target. This completes the first segment of the program. Now it's time to work the exercises in your workbook. Stop the tape and turn to Workbook Period 1. A variety of different instruments can be used to carry out the measurement and control jobs in a process plant. It's easier to understand how these instruments relate if we can group them into 4 general categories. One group of instruments consists of devices that sense or measure process variables like temperature or pressure, or they cause a change in the variable so it can be measured by another instrument. These instruments are usually called primary elements or sensors. The devices in this group that are installed directly in process flow lines and process vessels are usually referred to as primary elements. This orifice plate is a primary element for flow measurement. A thermocouple is another type of primary element. It's used in making temperature measurements. This helical-shaped Bourdon tube, used in making pressure measurements, is connected to a process flow line by the metal tubing at the bottom of the element. Devices of this type are often called sensors or sensing elements because they change shape, size, or position whenever a process variable changes. Transmitters are another group of instruments. A transmitter gets information from a primary element or sensor and then transmits a measurement signal. Either electricity or compressed air is generally used to transmit these signals. So when we talk about a measuring means, we're usually talking about a primary element or sensor coupled with a transmitter. This is an example of a field-mounted transmitter that transmits flow rate measurements. Controllers are the next group of instruments. Controllers tell valves what action to take. A control mechanism inside a controller receives the measurement signals from a transmitter. After comparing the measurement with a desired value, the controller transmits a signal to a valve or other final control element. So, a controller consists of a comparing mechanism and a transmitter combined in the same housing. But there are several different types of controllers. Some are mounted in the field, like this, while others are mounted away from a process at a central control area. And still others are connected to computer control systems, which provide faster, more precise control. Some controllers record process information on charts. Other controllers simply indicate the current condition of the process variable being controlled. There are also instruments that move or actuate valve stems. These are called actuators. Actuators receive signals from a controller. Here's a valve with an actuator. The pancake-shaped device on top of the supporting yoke contains a diaphragm. The diaphragm is operated by compressed air, and it moves the valve stem up or down. Now, look at this valve. The black box with the 3 pressure gauges installed on the actuator yoke is called a valve positioner. Sometimes the maximum compressed air signal a controller produces isn't sufficient to move a valve stem or to move it fast enough. In these situations, a positioner helps the actuator move the valve stem. Let's look again at the 4 things that are needed in any control situation. First, there is a process that needs control. There is a measuring means. This usually consists of a primary element or sensor coupled with a transmitter that transmits a measurement signal. There is a control mechanism, which usually consists of a comparing mechanism and a transmitter together in the same housing. In a process situation, this device is called a controller. And there is a final control element. In process operations, the final control element is usually a valve with an actuator. In a control situation, we always need the 4 basic elements named on the left of this chart. The things named on the right perform the actual jobs in process plants. Almost any instrument in the 4 basic groups we identified can be connected to some type of indicator. For example, this field-mounted controller has a temperature indicating scale. The gauge at the bottom left of this controller tells us how much compressed air is supplied to the instrument, and the gauge at the bottom right tells us how much compressed air is being sent from the controller to the diaphragm actuator on a control valve. Let's take a look now at some typical process instruments. Stop the tape and turn to Workbook Period 2. You learned that 4 things are essential to any control situation. These 4 elements are called a control loop. Let's use some of the instruments you saw in the previous workbook period for a review of how the parts of the control loop work as a team. Assume the process we are controlling is one of these gas-fired furnaces. The furnace heats crude oil before the oil enters the process vessel. The variable we want to control is the temperature of the crude. We need a primary element or sensor so we can get measurement information. Here we're using a thermocouple installed in the oil flow line. We need a transmitter that will interpret information from the thermocouple and transmit it to the controller. We can use a transmitter like this one that is built into the thermocouple housing. And we need a controller like one of these to receive the measurement signals and compare them with a desired value. A valve like this one is the final control element in the loop. The valve regulates the flow of fuel gas to the furnace. If oil temperature rises, the valve will get a signal to decrease the gas supply. If oil temperature drops, the valve will increase the amount of gas to the furnace. It's important to remember that all the parts of the control loop send or receive signals continuously. But the valve stem does not move unless these signals change, which would indicate an increase or decrease in temperature. Let's consider an example. Suppose oil temperature decreases. The thermocouple senses this change. The signal the thermocouple sends the transmitter changes, and this changes the signal the transmitter is sending to the controller. The controller compares the transmitter signal with a value that represents the desired oil temperature. Normally, these 2 values should match, but in our example, the 2 values are not the same because oil temperature has decreased. The controller determines that the control valve should open more, and it tells the valve to increase the gas supply. The valve opens more, and this corrective action causes the temperature to rise. This change in temperature is sensed by the thermocouple and transmitted to the controller. Again, the controller compares a reference value with the transmitter's measurement signal. If the 2 values are the same, the controller continues to send the same signal to the control valve. If the 2 values still do not match, the controller again changes the signal transmitted to the valve. The controller continues to adjust the valve until the controller's reference signal and the signal from the transmitter are the same. Let's review these control loop actions. First, process temperature decreases. The measurement device senses the change in temperature. This is transmitted to the controller as a change in temperature measurement. The change in temperature measurement causes the controller to change the signal it sends the valve. The controller tells the valve to open more and increase the gas supply to the furnace. The increased gas supply causes temperature to rise. The controller detects this measurement change. If necessary, the controller changes the valve position again. After the controller takes corrective action and the valve moves, the information that reaches the controller is called feedback. Feedback lets the controller know that its corrective signal has caused a change in the position of the final control element and a change in the process variable. Because signals move through the control loop continuously and can be changed as necessary, feedback is possible. In every control situation, it is assumed that there is a desired value for each process variable. This appropriate value, or range of values, represents the best available operating condition for each variable at that particular process. The desired value for a process variable is usually called set point. Here are some values that could represent set points for some process variables. We usually express a set point value as a specific number or as a percent of a particular number or range of numbers. At many controllers, a process pointer indicates the actual condition of the variable controlled by that controller, and another pointer indicates the set point value for which the controller is adjusted. On computer systems, the condition of the variable and its set point are often shown graphically. An operating manual or other operating instructions for each process unit should identify the set point for each variable in a particular process. So, the main job of a control loop is to keep a given process variable at its set point. And the set point for each variable is determined by what conditions will produce the desired end product. It's time now for us to review control loops. Stop the tape and turn to period 3 in your workbook. In most process plants, the instruments that control the process are here in a central control room. But the instruments that actually measure process variables and move valves are out here in the process area, several hundred feet away. So some method of connecting the instruments and transmitting signals is necessary. One way to transmit signals is through pneumatic lines like these. In a pneumatic transmission system, changes in the pressure of air inside tubing is used to transmit signals. For example, the air inside this tube is at a uniform 9 pounds per square inch. Now, suppose air at 15 pounds per square inch is fed into the left-hand end of the tube. Almost instantly, this wave of higher pressure air moves towards the area of lower pressure air to equalize the pressure. A message has been transmitted from one part of the tube to another. We can understand this message by reading the gauges and noting the increase in tube air pressure. Suppose we connect the parts of a control loop with pneumatic tubing. Assume our control loop controls flow, although it could be any variable. At the transmitter, compressed air at a constant pressure is continuously fed into an instrument supply air line. The flow information the transmitter receives through the tubing determines how much of the supply air is allowed to pass through the outlet line to the controller. If the flow increases, so does the air pressure passing into the outlet line. The controller compares the compressed air signals from the transmitter with a reference signal representing set point. The reference signal is produced by giving the controller its own air supply and then restricting the supply by a certain amount. An air line from the controller connects with the valve actuator. After the controller compares the transmitter signal with the set point reference signal, the controller determines how much compressed air should pass from the controller to the valve. The amount of compressed air going to the valve changes only if there is a change in the flow measurement. The compressed air signal from the controller determines the position of the valve actuator, and as a result, the valve stem. Many control systems use electricity sent through wires instead of compressed air inside tubing. Electrical signals are faster and can move longer distances than pneumatic signals. Let's look at an example. The variable we want to control in this situation is the tank pressure. Our sensing or measuring instrument is a diaphragm located inside a pressure transmitter. The diaphragm is attached to an electronic sensor that sends electrical signals to a controller. The position of the diaphragm determines how strong a signal is sent. Now, suppose pressure in the vessel increases. This will cause the diaphragm to expand, and the sensor, in turn, will send out a different electrical signal to the controller. The controller compares this new electrical signal with its own set point reference signal. Since the signals don't match, the controller will signal the valve on the outlet gas line to change position. In our example, the controller will signal the valve to open further. This allows more gas to flow out of the vessel, thus reducing the tank pressure. Even when electrical transmission is used, valves and some system instruments are usually still activated by compressed air. To convert electrical signals to compressed air, we use a device called a transducer. Transducers allow us to tie electrical and pneumatic transmission systems together. The trend in process instrumentation is towards more electronics. That's because electrical transmission systems are generally more accurate and can more easily interface with computers. Let's stop now and take a closer look at pneumatic and electrical transmission of control loop signals. Stop the tape and turn to Workbook Period 4. Some process control rooms use charts to show the flow of materials entering and leaving a process. They also show where instruments and valves are located and how control loops are arranged. This kind of chart is often referred to as a process graphic. A process flow sheet of this type is used by contractors when process equipment is installed, and it's used for reference by maintenance and operations personnel after a process is put on stream. Symbols and outline drawings of process equipment like these are used on some process blueprints, flow sheets, and charts that you may see and use in your job. Symbols are used to indicate and identify instruments and valves. Through a series of letters and numbers, each symbol will tell you the variable that is sensed, measured, or controlled by that instrument or valve, whether the instrument records, indicates, or performs a similar function, and the type or name of the instrument or valve. The letter identification for an instrument symbol is usually arranged in this order. A circle indicates the instrument. The letter of the variable being controlled appears to the left. If the instrument records or indicates, this is indicated by a middle letter. The letter on the right side tells you the instrument that does the job. The letters in this instrument symbol stand for temperature recording controller. The number of the control loop, if any, is shown in the bottom of the symbol. In a given process, there may be several loops controlling the same kind of variable, so each loop has its own number. Every instrument in a loop can be identified by the same loop number. Here is the symbol for another controller. The letter F stands for flow. Flow is the variable being controlled. The middle letter R stands for recording, and the end letter C stands for controller. So these letters tell us that the instrument is a flow recording controller. The loop number appears in the bottom of the symbol. A circle like the one on the left with a line drawn through the center is a panel or board-mounted instrument. A circle like the one on the right indicates a field-mounted instrument. Valves are usually indicated by a symbol that looks like a bow tie. A process flow line is drawn through the valve symbol. A half circle connected by a short line to the valve symbol indicates a diaphragm actuator. In other words, this valve is operated by pneumatic signals. For instrument symbols, the letters and numbers are written inside the circle that indicates the instrument. For valves, the indicating letters can be enclosed in a circle next to the valve symbol, like this. These letters stand for flow control valve. Valves that are part of an automatic control loop are called control valves, and the letter C is always the middle letter in the valve symbol. Let's review the location of indicating letters. The letter for the process variable is always first. If the instrument indicates, records, or performs some other function, or if the device is a control valve, there should be a middle letter to indicate this. Last, there's a letter that stands for the actual name or function of the instrument. The letter symbols for the names of process variables are usually made from the first letter of each name. Here are the letter symbols for the 4 most common process variables. Here are some possible middle letters for instrument symbols. The letter C is used for control valves. The other letters are used with indicators, transmitters, and alarms. If a controller is a blind controller, there is usually no middle letter in the symbol. For example, this symbol indicates a temperature controller that doesn't record or indicate. These are some of the letters used to indicate the names of instruments. The letter V is used to indicate a valve. The letter A can indicate either an analyzer or alarm. When A is placed after another letter, like the first example, it usually means an alarm. If the letter A is placed in front of another letter, like the second example, it usually indicates an analyzing instrument. Process piping and the walls of process vessels are usually shown as solid, unbroken lines. The lines supplying air to process instruments are shown by short diagonal marks crossing a solid line. Here, a valve is connected to a controller by an air line. Electrical signals and electricity supplied to instruments are indicated by dotted or dashed lines. These symbols show a thermocouple, the electrical wiring between the thermocouple and a transmitter, and a pneumatic air line from the transmitter to a controller. These symbols show a temperature indicator, an industrial thermometer connected to an indicating gauge. The gauge is connected to the thermometer by capillary tubing. In other words, a liquid or gas expands or contracts inside the tubing, and this indicates temperature. The capillary tubing is shown by a line crossed with a series of X's. To review, here is a complete control loop depicted by instrument symbols. The primary element is an orifice plate. This is shown by the 3 lines that interrupt the solid line for piping in the lower left of the drawing. 2 pressure taps connect the piping with a differential pressure transmitter, which is marked FT for flow transmitter. Electrical wires connect the transmitter to a board-mounted flow recording controller. Electrical wires also connect the controller to a diaphragm-actuated flow control valve. The symbols we've shown are like those commonly used in the process industry. However, you may see some minor variations between the symbols in this program and the ones in your plant. The charts and diagrams may also vary slightly, as many companies omit some symbols to make the diagrams easier to read. Now, stop the tape and turn to Workbook Period 5. You learned in the program that the main purpose of a control loop is to keep a given process variable at its set point. When a process variable deviates from its set point, there are usually several possible causes. But no matter what the cause, control loop instrumentation must try to prevent the problem from affecting process variables. A common term for a process problem that may affect one or more process variables is process upset. An upset is generally defined as any major change in process conditions that could result in unsafe operating conditions, or that produces a product that is off specifications, or both. The following are examples of process upsets. As we go through them, try and determine which ones cannot be returned to set point by automatic controls. Here's a situation that could cause a process upset. Normally, fluid flows into this tank from a process and then from the tank into a chemical processing facility. Suppose someone closes the manual block valve on the inlet line to the tank without notifying the unit supervisor. Since no fluid is entering the storage tank, the level begins to drop as fluid is pumped out and sent to the chemical facility. Fluid isn't leaving the process, so process fluid level increases. The control loop for process fluid level opens the control valve on the outlet line as wide as possible, but still no fluid leaves the process. If the manual block valve to the storage tank isn't opened, it may be necessary to shut down the process. Here's another problem. A pump supplies one process vessel with fluid from another process. The pump has a mechanical failure. No fluid is being pumped out of process A, and pressure and fluid level increase. No fluid is entering process B, so pressure and fluid level begin to drop. Now look at this situation. One of these furnaces heats process fluid that flows through the furnace inside a pipe. There is a temporary fluctuation in the amount of fuel supplied to the furnace jets. This causes a temporary drop in furnace temperature and a drop in fluid temperature. In another problem, the foreman for this crude oil distillation unit gets instructions to raise production by 50 barrels per hour during his shift. As the unit operator increases feed, he must also take some other things into consideration. For example, if he increases feed too fast without also increasing the reboiler fuel supply some, a drop in process bottom temperature results. This list names the examples of process upsets we just described. In two of the examples, the process cannot be returned to set point by automatic controls. Decide which two examples they are. If you decided storage tank and the pump failure, you were correct. In the example of the storage tank, fluid couldn't enter the tank and fluid couldn't leave the process vessel because of the closed block valve. Automatic instruments couldn't do anything but open the valve on the process outlet line as wide as possible, although that didn't help. Automatic instruments can't compensate for a mechanical pump failure either. It might be necessary to shut down both these processes if a spare pump isn't available. A process operator should understand that automatic process instruments can't always return a process variable to its set point. This is why an operator must continually pay attention to controllers and other indicating instruments. An operator may find it necessary to make process adjustments manually if a process upset occurs. In a situation like the failed pump or the closed valve, an operator would probably be signaled by a buzzer alarm or warning lights indicating that a process variable is above or below its safe operating range. We've covered a lot of information in this first instrumentation program. You've learned that controlling a process is a matter of controlling its variables. When we control the variables in a process, we're able to produce products that meet the specifications we want. You have also learned that no matter what the variable and no matter what the control situation, four basic elements are usually needed. First, there is a process that needs measurement and control. There must be one or more instruments as a measuring means that senses and measures the variable being controlled. The measuring means also transmits a measurement signal. A controller compares the measurement signal with a desired value called a set point. Then the controller transmits a signal to the final control element. The final control element makes the actual process adjustments which the controller determines are necessary. In process plants, the final control element is usually a valve with an actuator. These four elements are called a control loop. A modern continuous processing facility like this one has hundreds of control loops, hundreds of valves, and many variables under control all at the same time. It wouldn't be possible to control all of the variables manually. Automatic process instruments make continuous processing and continuous control possible, and they provide process operators with up-to-the-minute information on the status of every process condition. This concludes the video portion of the program. Be sure you work through the exercises in Workbook Period 6. Thank you for watching.